Okay, let me share my screen and start. Yeah, so I just asked about transformers. It's not necessary to know it for this talk, and on this talk I won't be covering it, but just to understand how familiar you are. But yeah, as I said, it's not a prerequisite for this talk. Can you see my screen? Oh, let me try sharing it just like this. Can you see my screen now? Okay, cool. So yeah, so I picked a very provocative name for this presentation. Why GPT is better than BERT. In no way, I mean, it's like in no way it's true for everything, but I will explain what I mean by this through this presentation. And you can write in chat, but actually when I present in my screen, it's hard to see the chat. So since you are a small group, you feel free to just unmute yourself and ask questions if something is not clear. But the topic is why GPT is better than BERT. Like to start with, let me just tell a bit about myself. So actually my background, educational background is in physics. I did PhD in condensed matter physics, but later I moved to finance, and currently I work at Deutsche Bank and building some trading algorithm. So you see, I'm not really from the field of NLP, natural language processing, and I'm not a deep learning. I'm not in the profession of deep learning, but this is something that is very interesting to me, and something that I've been following, especially with the emergence of ChatGPT, the very disruptive technology, and yeah, some things that I couldn't understand. I was looking into them and trying to build some picture for myself, and this is what I want to share with you today. So the content of this presentation is the following. So first of all, of course, I'll outline what is the purpose of this talk, and I'll just tell you which questions I will try to answer. Second thing, I will start this slow, gentle introduction by discussing a very a simpler model than BERT and GPT, word-to-vec, and this model is was not designed for actual encoding or working with sentences. It was designed to find the encoding for individual words. So the idea there is just to find a vector representation for every word. And yeah, then gently I'll move to BERT, which is a model that fixes some shortcoming of word-to-vec, and I'll cover the insights that this model brings, and I'll cover the details of this model. And then I'll move to GPT, and of course I also discuss some details about it. But the main thing that I want to answer is why actually this is the architecture that people are now using for very large models. And this is the question that I'm trying to answer: why GPT proved to be better than BERT for this kind of models. So let's move to the first part, the purpose of the talk. So my motivation is really, first of all, BERT and GPT were very transformative models. So and even though they were very transformative and very widely used, they are actually very different. And it's very surprising to have two different models that are also successful at the same time. And it's important, I think it's interesting to understand why they became successful, so what insights they brought, but also it's interesting to understand, looking into the model details, what is the differences between those two models, and this will help us to answer the following question. The next question, so in the end we want to answer why now most large language models actually use GPT architecture and not BERT. So let's move to the introduction. So let's start with a simpler model. It's called word-to-vec. It was introduced by Google in 2013. And the idea, as I briefly mentioned before, is to find some vector representation for every word. So you can think about all the words that we have, the dictionary of the words. It's like tens of thousands of words, but we want to reduce this 10,000 dimension to something smaller. We want to bring words to some smaller vector space, and we want to find this more efficient representation using less variables. And hopefully we will have some insights from this. Hopefully we will be able to this way encode the meaning of the word. And potential application, if you have the meaning of every word in the form of vector, and you have some sentence or you have some tweet, and you want to understand if this tweet is good or bad, or you want to understand if this sentence about cats or dogs, you can just sum up all the vectors and take the average of them, and this will give you the average meaning of the sentence. So there are applications for this exercise, and now let's understand how it was done. So it's not beforehand, it's not clear how you want to define this transformation for every word, to map every word to some vector. And it's important to find some problem setup that is very clear, very simple, and also at the same time, what is key for machine learning and for deep learning, it allows for optimization. So you can formulate the problem in the way that allows you to find the best possible representation of words as vectors. So this is a challenge, and how this challenge was addressed. So let's discuss this. So let's look at the sentence, I saw a cute gray cat playing in the garden. So, let's think how we want to, and how we can understand the meaning of the word gray. The meaning of the word gray, overall, it can be understood from the context of the words, from the words that are appearing in the context of this word frequently. So we can can define a probability of all different words appearing in the context of the word gray. And we see here, for this specific sentence, we have a, cute, cat, playing. So these four words, they are in the context of the word gray. And they somehow should define its meaning. And of course, it's not the only sentence we are looking at. Imagine we just have thousands or hundreds of thousands of different sentences, and we see gray in some other sentences, and it has different context. But overall, the combination of all these contexts should define the meaning of the word gray. So we would write the probability of seeing this context as the following. We will split it into individual probabilities. So you see the formula at the up. So we multiply probabilities of seeing the word A, the word cute, and the word cat, and the word plane in the context of the word gray. So this kind of quantities we will be trying, we need to multiply to get probability of seeing this whole context of the word gray. And
one quick thing to point out, I think there might be an issue with your presentation. We can only see your title page, the initial.
Oh my God.
So we can't see that.
Oh, apologies.
Yeah, no worries.
Thank you for pointing this out. Probably when I do full screen, you can't see it, but let me just. So now you can see it scrolling, right?
Yes, we can see you scrolling.
Oh, sorry, apologies. Thank you for pointing this out. So yeah, let me start over with the slide because it's important. So yeah, word to vec is just approach to transform like words to vectors, and as I said, so we have let's say dictionary of tens of thousands of words, and we want to put them in some space where we can compare them or do some operations with them. For example, if you have a vector of one word that encodes its meaning, to understand the meaning of the sentence, we can just take an average of all the words in the sentence, and this will roughly give us the meaning of this sentence. And we can use this later for some classifications or other tasks. Okay, but how we actually can put, how we can do this transformation? And the first, the idea is to find a problem setup that will allow us to find optimal transformation. And the problem setup is, we can look at this sentence that we have. I saw a cute gray cat playing in the garden. And we want to find a representation, better representation of the word gray. So the representation that will encode the meaning of the word gray. And one very interesting move, I think, very interesting idea is to say, okay, actually the meaning of the word gray is encoded by the words that we see in its context more frequently. And we have a huge, let's say, number of sentences, like let's say hundreds of thousands, and gray appears there like thousands or maybe tens of thousands times in different contexts. And if we see all possible contexts in which this word appears, we can actually figure out what is the meaning of this word. For example, if we see word gray appearing in some sentences, but the word black will be appearing in similar sentences, we can figure out that gray and black, they are kind of somehow related, or with any other color. So how we formalize it? Let's look at the following probabilities. The probability of seeing the context given the word gray, and we do simplification. We split this probability as a product of independent probabilities. So the probability of seeing the word A in the context of gray, cute, cat, and plain. And what we want to do, we want to find an approximation for this probability that will maximize the overall probability over the whole text. And we will use the formula on the right to approximate each individual probability. So we will basically take, we have a green vector V and a gray vector U. V represent the center word, the gray, and U represents outside the word, is A, cute, cat, or plain. And each probability, and those U and V, they are vectors, and they are actually the embeddings that we are looking for. So we will represent each probability this way. We put this formula on the right into the expression on the left. We do it for the whole text that we have, for the whole data corpus that we have, and we try to maximize this probability. So we try to find the vectors U and V for every word that will maximize this total probability. And in the end, our hope is to find the vectors that encode each word in the best possible way and the most efficient possible way. One thing that I want to point out here is that in machine learning, people typically split problems in supervised and unsupervised. Here, this problem would be called unsupervised learning because we don't need any human input. So we don't need human to go and label this data. We just need the data, and the data itself contains all the information we need. Because, for example, in this case, we have the word gray, we have its context, we don't need any human input. And this idea of maximizing total probability, which is effectively unsupervised setup, is what will be used in the later models as well. But now let's summarize word to vec. Now let's discuss what are the results of this model and what are the problems that we would want to overcome. So what is nice is that the framework is very clear, it's optimizable, and the results actually turn out to be interpretable. So what I mean? So what is nice about framework? It's like as I said, it's very useful if you find these vector representations. You can actually use it for some classifications problems. If you just take an average of all words in the sentence, you can get the meaning of the sentence. But also there is some nice emergent property. I was giving an example that gray and black will become similar, but for example, vector for the word puppy will become the vector for the word dog plus difference of kitten minus cat, because kitten minus cat would represent, let's say, small animal, and dog plus small animal in terms of meaning would mean puppy. So this is something that was not expected, but this turned out to be true. So this, by embedding each word in this form of vector, we get this with this mass working, the mass of different meanings. So we can subtract, add meanings, and the word will transform in another word with the meanings that we added. So it's very, very interesting. But what is the limitation of this approach? It turns out that each word will have a single representation. And it doesn't matter which context we put this word in, it will still have the same vector representation. And this is not always correct, because in the simple example would be the words that have different meanings depending on the context. So look at these two expressions, data type and type using keyboard. The word type in these two contexts have different meaning. But if we use word embedding for word-to-vec approach to them, we will find the same vector representation. We will use the same vector representation. So the key here, or the missing part here, is actually to look at the context for the word to get better idea of what it means. So, and here at this stage, we just move into BERT. So let's discuss this model. So this actually was also done by Google in 2018. And the idea here is actually to solve the problem that I was just mentioning. You want to find word embedding, word vector representation, given a context of the word. And again, here the setup will be used unsupervised. So we again just have our data set is just all possible text that we find useful, that we find not dirty, and we want to use for our model, and we don't need any human input. So how's this done actually in BERT? So let's look at the input. So at the bottom. At the bottom we see let's stick to improvisation in this skip. So we want to find encoding for the word improvisation, and how we set up the optimization problem to do this. What we do, we just take every sentence and randomly mask some of the words. In this context, let's mask the word improvisation. By masking, I mean that we don't let model see it. But what we want model to do, we want model to guess what was the word there. And the model is producing results, producing its guess, and the BERT. And in the end, we want this guess to be as close as possible to the correct word. So we want to maximize the probability predicted by the model of the correct word. So in this case, we put this mask sequence through BERT, and we want BERT to predict that word improvisation is with high probability at this position. So it's very interesting idea. And then again, similar to word-to-vec, we just take all possible sentences that we have, we apply some different masks, we predict probability of the word, of the correct word, and we try to maximize this probability. And this is the optimization that happens. So the parameters of the models are tuned to maximize the probability to predict the correct word. And again, this is what makes this unsupervised. We just don't need any human input, we just need text. And the architecture for BERT, just a side note, it's called encoder only. And it means, and it's in transformer, or not even in transformer, in natural language processing world, there are always these terms decoder, encoder, encoder, decoder, and just for maybe your education and just for the context, this architecture is encoder only. And what it means, encoder means that it allows to see all the words. What I mean is, we mask the word improvisation, but we allow BERT to see both words that are coming before this word and all the words that are coming after. So this is why it's called encoder. However, one thing that is very important here and will become important for comparing with GPT, you see that at one step of optimization, we were masking just one word. And and effectively, we took whole sentence, did some manipulations on the sentence just to predict probability of one word. So at one step of optimization, we just can predict one word. This is what is the property of the BERT given this problem setup. Let's keep it in mind, and it will become useful later. So what are insights actually of BERT? Because again, even though maybe this is a little bit less hyped model now within ChatGPT era, BERT is still widely used, and at the time when it was introduced, it brought a lot of insights. So the main insight, I think, is that the fact that we were trying to predict the word in the context. We were trying to predict, generate embedding of the word given the context. But to properly generate the meaning of the word in the context, we also need to understand the context. So somehow solving a simpler problem of predicting the word, we teach the model, we force the model to understand the context. So this is actually a very powerful thing. Effectively now, our model is able to understand the whole text. It's and the fact that the training that we use is unsupervised, so it doesn't depend on any human labeling. It makes it non-task specific. So it means that we didn't really try to optimize model for any task. We just trained model so it just understands the text. And the result of this is that BERT is actually became a general purpose model. So people use it for very different applications because it has capabilities of understanding effectively any text, whatever problem people have for text understanding, they can apply BERT to it. For example, the obvious one is classification, but also people use for, let's say, understanding if, let's say, you have some email and you need to parse it to extract certain entities. For example, is the client, how much client paid to you, and BERT can be used for this problem as well, and also many other things. So it's a very useful and very insightful thing that you can just train model in non-task specific way, and this makes model applicable to many tasks. Obviously, in some cases, if you train task-specific model, it will perform better. But as we know, training model can be expensive. So it's also it's very useful to have some general purpose model that's already trained and that you can apply to many different tasks. So, and the limitation that we just discussed on the previous slide was that on one optimization step, we just cover one mask configuration. So it means that we did calculations with the whole sentence, and let's say our sentence or our context is of the length like hundreds or thousands of words. So we did calculations on thousands of words, but to just predict one mask configuration, which seems suboptimal. And so we don't use many calculations that we did. And at this point, it actually brings us to GPT. By the way, GPT stands for Generative Pre-trained Transformer. I think it's not that important what it actually stands for. We will discuss, we won't dive into those details, but we will cover the part that is generative. And we will understand why GPT became the primary architecture for very large models. So GPT was introduced by OpenAI, and I mentioned 3 dates here is 2018, 2020, and 2022. And these 3 days, they correspond to different versions of GPT from OpenAI, GPT-1, GPT-2, and GPT-3. And the idea of GPT is similar to BERT here. So, but still, there is a difference. So you try to predict what will be the next word. Rather than mask word in a sentence, you try to predict, given your history, given your past words, previous words, you try to predict the next word. So in this case, robot must obey orders. So we will give the model robot must obey, and we expect it to predict orders. And same as with BERT, we want to find the parameters of the models in the way that they will maximize the probability of the word orders. This kind of architecture is called decoder only. In contrast with encoder, decoder is only allowed to see all preceding words. So it's not allowed to see the words that are following the word orders. But the advantage of decoder only architecture is the following. So on this picture, we see how we predict only one word. But in reality, due to actually structure of GPUs, of hardware, the calculations are done in the way that when you run this GPT on one sentence, it will actually produce predictions for the next word for each of the words in the sentence. So along with the orders, we will try to predict the word obey after the must. We will try to predict the word must after the robot, and the word robot after the start of the sentence. And so in contrast with BERT, we use all the words in our context, and we do predictions for all the words in our context, which makes it kind of more efficient because we are not throwing any calculations away. And again, so here generate, it's exactly comes from generative pre-trained transformer, so the part generative. So because we are generating the text. Okay, and then the question is, okay, they are more efficient, but is there any benefit for being more efficient? It turns out it is. So I will talk about the insights that we obtained or we presented in GPT-3 paper, it's when actually the model became really large. And it's possible to produce a very large model only if you can train it efficiently, because this is what becomes the bottleneck. And probably you heard as well that to train models for ChatGPT, OpenAI, and other companies who train similar models, they would spend tens or even maybe hundreds of millions of dollars just to train the model, because it is so expensive computationally, and you need a lot of hardware. So training the model efficiently actually allows to scale your model. And the GPT-3 was trained with 175 billion parameters. In contrast with BERT, that was the typical size of BERT-like models is hundreds of millions of parameters. So there is a difference in the factor of 1,000. So the GPT efficiency allows to go by 1,000 with 1,000 more parameters to train. And the question is, do we need these models to be big? The answer is yes. It turned out that with increasing the model size, the new emergent properties appear. And one very interesting property called few-shot learning. And what does it mean? So let's look at the screenshot on the right side. We can just give the model a text, translate English to French, then we give word cheese, and we should expect model to understand what we needed to produce. So this is zero shot, meaning that we don't even give a single example, and model immediately understands from the context what it needs to do. It can predict, because it's generative, it can generate the next word correctly. And one shot, it means you need to give one example. Few shot, you need to give few examples. But given these few examples, you actually precondition your model to be able to generate the correct response to what you produce, to what you wanted to see. And this kind of capability, it is really amazing that it appeared, because if you look at the chart on the left, you see that depending on the size of the model, you see 1.3 billion, 13 billion, and 175 billion parameters. You can have or you can have not this capability. For example, 1.3 billion parameters model had very poor accuracy, like under 5% in solving this kind of tasks, while 13 billion was dramatically better and 175 billion was even better. So it turned out that this efficiency of training GPTs is actually critical, because you can train bigger models, and bigger models, indeed, they give you much more power, and they are indeed much more powerful. So with this, I actually want to wrap up, and I just want to repeat most important points and most important insights from my point of view. The one thing that is just interesting is that by focusing on the problem of predicting the word, you actually force the model to understand the text, to understand the whole text, because the only way you can predict word efficiently if you understand the context. Also, another thing that applies also to both BERT and GPT, and as well word2vec, is if you do unsupervised learning training. So if you train model without any task-specific labeling, you just train it to predict well the text that you have, it becomes a general purpose model. It can be used for many different applications. And for example, with ChatGPT, we see that it was not trained, using ChatGPT's example, it wasn't trained to do translations. It wasn't trained to write essays. It wasn't trained to do some summarization of the text. But this somehow emerged as the fact that it was just able to predict the next word, and it became aware, and it became capable of understanding the text and understanding the task that is given. So it is very interesting, because previous approaches were always to train model specifically for the task. Okay, and then the answer to my question, effectively, why GPT is better than BERT, in the context of very large models and very powerful models, GPT is indeed better, because its training is more efficient, and thus it's became a primary choice for very large models. Thank you. At this point, I want just to mention additional resources, and these resources that I was using to prepare this. And I would refer you to just check original papers with BERT and GPT just to see. I think it's just all very curious to see how researchers were presenting it at that time. And also, those papers are pretty approachable in my opinion, so you can check those. But also I want to highlight two blogs that I was using for illustrations. It's NLP course and the Illustrated Transformer. Okay, thank you. Let's move to questions. Yeah, let me know in the chat or via voice if you have any questions.
Hi, random question. So talking about how BERT is trained with random masking, do you think that that means that it would be better or different if you were to try to make a vector database using encodings from BERT versus a GPT encoder or decoder?
Okay. Can you say once again?
Do you think BERT would be better for creating a vector database with it? So creating embeddings and then using those embeddings to find similarities and storing documents based on those similarities.
Okay, got it. So you're basically saying, is BERT efficient in creating embeddings for the documents? Is it better model than GPT? Yeah, actually, I don't really know what other. I know that this is something that is used. So people actually produce these vectors for documents, and this allows, for example, you can ask a question, it will be encoded somehow, but from this embedding you can actually try to find the relevant document. But I'm actually not sure what models are used to generate these embeddings for documents. I would think that both GPT, because GPT it has its running state, and you can take just its state at the last point, or you can take GPT's let's say average of all the words. So GPT is capable of producing these embeddings. Also, BERT is capable of doing so because BERT is actually it has an interesting property. Let me share my screen again. I didn't mention it. Oh. So BERT has very interesting property that they specifically, when doing the model, they create a special token. It's like for classification, and this special token is supposed to have embedding of the whole text. So I would say that both GPT and BERT can produce embedding of the whole text, but maybe given that BERT has a special token for which the whole meaning of the text is supposed to be encoded, I would think that it's more like designed for producing this vector database for the documents. Yeah, I'm actually interested to hear your thoughts on this as well.
I'm not sure. I'm still trying to understand the difference between the encoder and the decoder. I had been under the impression for a long time that GPT used both an encoder and a decoder, and I think I was surprised to learn a couple weeks ago that it uses only decoders.
Yeah, I think what I like about this is that it makes kind of the setup simpler. Of course, simpler is not always better, but if simpler and better, it's nice. So this is what I like about GPT, that instead of having kind of these two different blocks, encoder and decoder, it can operate just with encoder. And but just with the decoder. And I can see where this confusion is coming from, why you expect both encoder and decoder, because when you ask ChatGPT a question, you expect it to use one model to take representation of your question, and then produce an answer using decoder. And it's surprising that you can do this kind of things just with one model, with decoder. So it both reads your question and generate the answer. Yeah, indeed, it's surprising, but I think this makes the setup simpler, and maybe just from practical training purpose point of view, this is why it just became decoder only, because it's just simpler. Thank you for your question. Yeah, feel free to also ask questions on the chat. I know it's just 3 of you, and I can't expect a lot of questions, but yeah, we have 5 more minutes, and we can just chat about this if you're interested. Carl, and is your background in machine learning?
No, my background's in physics, and I'm a software engineer now.
Okay.
But I've been interested in NLP for a while, so I've been reading a lot about this stuff, and yeah, trying to make sure I understand it.
I think same for me. Cool. If there are no questions, yeah, feel free. I left a link, so not link, but my tag, so you can just, if you want, you can connect with me on LinkedIn. But yeah, if nothing else, yeah, thank you for your time. Thank you for joining. Bye-bye.
Thanks for presenting. Take care.